Hello, this is Matthew from the UNT Dallas Math Lab, and today we'll be going over normal distribution. So before we get into normal distribution, we'll have to go over some vocabulary. Let's say if I gave you a bunch of IQ scores, and you wanted to see where your IQ score ranked amongst everyone else's. So you're going to test your IQ score versus everyone else's. So that IQ score that you're testing for, your IQ score, that's going to be the critical value because that's the threshold that's being tested. If I gave you, let's say, 10 IQ scores, and you wanted to find the mean or the average, that's the middle, that middle IQ score. You're going to have to add, it's going to be the sum of all IQ scores divided by the number of IQ scores. So I gave you 10, so it's going to be the sum of all the IQ scores divided by 10, or the sample size. So the sample size for those 10 IQ scores is going to be 10, because that's the number of IQ scores there are. Now the standard deviation is normally going to be given to you in the problem. The standard error is like the standard deviation in that it measures like the deviation or the accuracy of the sample. With the error, the standard error, you're kind of measuring the accuracy of the calculations. And the standard error is going to change depending on the type of problem you're dealing with. So in a couple slides, we'll be going over a couple standard error formula. Now, some problems, they'll ask you to find the critical value, or you'll be testing a critical value to find a percentage or probability of it being that critical value or more, or that critical value or less than. And then there's other problems that will ask you to find the confidence interval, or just like the probability. Let's say an area of your curve is going to be 90, so they're going to say find the 90% confidence interval. So you want to find that interval between what two numbers is that area going to be 0.9 or 90%. And that picture in the top right is going to be our normal curve. That's the standard curve, the bell curve. If I were to give you not 10 IQ scores, but let's say 1,000 IQ scores, they would be kind of displayed in this kind of graph, because you have on average you have more people in the middle, and then as you look towards the right or to the left, the number of people that have higher IQ scores or lower IQ scores decreases. So any kind of sample, if the sample size is high enough, the curve should look similar to that of the normal curve. So for our problems, and the most common, you'll be using the z-table. There's also the t-table and the chi-square table, and you'll use whichever table, whatever table you'll use. It depends on the problem. So if your sample size isn't high enough, you may need to use the t-table. If you're testing for standard deviation, you'll have to use the chi-square table. But for our problems, we'll be just using the z-table. And normally for the z-tables, you'll have two tables, one for the positive z values. So here I have the table for the positive z values. They go from 0 all the way to 3.69, and you'll have another table for the negative values. Along with the table and the percentages, the second most important part is going to be that picture at the very top. Because that kind of tells you what those percentages mean. So if you were to look at if you were to look at the percentage or the probability associated with the z-score or the z-value 1, it would be 0.8413. So what does that 0.8413 mean? That 0.8413 represents the area, that shaded area from z equals to 1 all the way to the left tail. In our standard curve, the area of the entire curve is going to be 1, because that's the highest probability. If you were to say something is for sure going to happen, it has a probability of 100%. It's going to be equal to 1. So the probability of flipping a heads on a coin is going to be 50% or 0.5. So it would make sense that for a z value of 1, for it to have 0.8413 because it's greater than 0.5, because half of my table, half of my curve is being halved in the middle, and if my total area is going to be 1, then half of it has to be 0.5. So if I'm looking at a z value that's to the right of the middle, and I'm measuring all the way to the left, that tells me that whatever my percentage is, whatever my probability is, it has to be greater than 0.5 because I'm measuring more than half. My shaded area is going to be more than half of the entire curve, the entire area under the curve. So to go along with that table, we'll need the z-score formula. And the z-score formula is going to be z-score z value is equal to x minus mu over standard error, where x is my critical value, or that threshold that's being tested or that's being tested for, minus mu, my average, all over standard error. And we'll go over the standard error formulas in the next slide. The z-score formula can be manipulated so that you get x by itself, and you'd want to use this whenever you're being asked to find that critical value, and we'll be doing that in a couple slides as well. So for standard error, I have 4 different formulas. Whenever you're given in your problem, you're given standard deviation, but if you're not given a sample size that ties together with your data set, you're just going to use standard error is equal to your standard deviation, or your sigma. If you're given a data set, if you're given your data set and you're given a sample size that's tied together with that data set, then you're going to take into account that sample size. So your standard error is going to be sigma, or standard deviation, divided by the square root of n, or your sample size. Now whenever you're dealing with one data set, you're given a sample size, but you're testing percentage values, like let's say you were doing binomial probability problems, or if you were doing something with probability like flipping a coin, how it's going to be 50-50, your p-value there would be that probability of that event occurring. So let's say you were trying to test for a head, if you were to land on heads when flipping a coin, it would be 0.5 because it's 50%. So your standard error there is going to be the square root of p times 1 minus p over n. So p is going to be the probability of that event occurring, and n is going to be your sample size. Now whenever you're dealing with any of the previous standard error formulas, but you're dealing with 2 data sets, you'll be using standard error is equal to the square root of the first standard error squared plus the second standard error squared. So if I was given 2 data sets, but I wasn't given a sample size for either data set, then my standard error for taking into account both data sets, my standard error is going to be equal to the square root of the first standard deviation squared plus the second standard deviation squared. And then, as always, for any kind of math problem, whether it's statistics, calculus, algebra, any kind of math, the best way to learn is by doing. So we'll be doing some example problems. Our first problem is: the amount of mustard dispensed from a machine at the hot dog emporium is normally distributed with a mean of 0.9 ounces and a standard deviation of 0.1 ounce. The machine is used 500 times. Approximately how many times will it be expected to dispense 1 or more ounces of mustard? So we're given quite a lot of information here. We're given the mean, 0.9 ounces. We're given the standard deviation, 0.1 ounce. They tell us a number. They tell us 500 times. It's not going to be the sample size, because it doesn't say that that mean and that standard deviation was taken from 500 uses. It just wants to know if it was used 500 times based on this information over there. Based on that information, if it was used 500 times, approximately how many times will it be expected to dispense 1 or more. So that 1 right there is our critical value, that threshold that we're testing for. So if I plug in all those numbers into my z-score formula, I have x minus mu over standard error. my x, my threshold that I'm testing for, is going to be 1. My mu, my average, is going to be 0.9. Standard error, because I'm just dealing with standard deviation, I'm not taking into account any sample size. My standard error is just going to be standard deviation, so 0.1. 1 minus 0.9 is 0.1. 0.1 divided by 0.1 is 1. So if I look up 1 in my z-score table, I get the probability 0.8413. But that probability 0.8413 represents what? That represents the area from 1 all the way to the left. But we're looking for when it's 1 or greater than. So we're looking not to the left, we need to look to the right. So what we can do is we can subtract that probability that we got from that table, that 0.8413, we can subtract that from 1. So we get that other piece on the other side. So we get, instead of from the left tail to 1, we get from 1 to the right tail. So after we do 1 minus 0.8413, we get 0.1587. So approximately 15.87% of the hot dogs are going to get dispensed with 1 ounce or more of mustard. So if we want to see, it's going to be 15.87% and 500 uses, we can just multiply that 15.87% times 500, and we get approximately about 80. So about 80 uses, after 500 uses, about 80 times you're going to get dispensed of 1 ounce or more. Another normal distribution problem. Entry to a certain university is determined by a national test. The scores on this test are normally distributed with a mean of 500 and a standard deviation of 100. Tom wants to be admitted to this university, and he knows that he must score better than at least 70% of the students who took the test. Tom takes the test and scores a 585. Will he be admitted to the university? So again, they give us our mean, they give us a standard deviation, and they give us a score. So they give us a threshold. So we can plug in all those numbers. We get 585, that threshold, that his score, minus 500, because 500 was the mean, over 100, because that was the standard deviation. And they didn't give us a sample size, so our standard deviation is our standard error. So 585 minus 500 over 100, that's going to be 0.85. If I look up 0.85 on my table, on my z-table, I get the probability 0.8023. So that 0.8023 represents the area from the left tail all the way up until 585. So that means that his score is better than 80% of everyone who took the test. So if he has to make a grade that's at least better, that's better than at least 70% of his other students, then he's going to get admitted because he was better than 80.23% of all the other students that took the test. So he'll be admitted to the university. In this normal distribution example problem, a battery lifetime is normally distributed for large samples. The mean lifetime is 500 days. The standard deviation is 50 days. To the nearest percent, what percent of batteries have lifetimes longer than 575 days? So again, we're given our mean, we're given a standard deviation, and we're given a critical value, 575. And they want to know what percent of batteries have lifetimes longer than 575. So that tells us again, we're not going to look to the left tail, we're going to look to the right tail. So I have my standard, I have my z-score formula, I have my x value, my critical value, 575, minus my mean, which is 500, over my standard deviation, which is going to be 50, and I get 1.5. I looked up my z-table, and I get 0.9332. Now the thing is, that 0.9332 represents from that 575 all the way to the left tail. We want to know from that 575 all the way to the right tail. We want to know the other side. So we'll have to do what we did before. We'll have to subtract that from 1. And this is kind of like the hardest part. So it's kind of determine whether that percentage or that probability that you got from the z-table, whether that's going to be your answer or if you need to do anything to it. So that's where drawing a picture will come in handy. some of the professors here at UNT Dallas, they say your first step when doing a statistics problem is draw a picture, because drawing a picture will help you, and I can't stress that enough. It will help you solve the problem. It'll help you see what you're trying to find. So we're looking for from 575 to the right tail because we want to know greater than what we were given, that 0.9332 from the table, that shows us to the left side. So we don't want that. We want to subtract that from 1, and we get 0.0668. So approximately 6.68% of batteries have a lifetime longer than 575 days. Now here's confidence interval problems, some confidence interval example problems. We have 500 values. They're normally distributed with a mean of 125 and a standard deviation of 10. So we want to find what percent of values lies in the interval 115 to 135. So I'm calculating the confidence interval between two numbers. So my first number is going to be 115. Second number is going to be 135. So I'm going to have to actually use the z-score formula twice. I'm going to use it once to find the probability from 115, and I'm going to use it again to find the probability from 135. So when I use it to find the probability from 115 all the way to the left, I get the probability 15.87%. When I use it to find the probability from 135 all the way to the left, I get the probability 84.13%. But I want to find the probability that's in between. So in order to find the probability that's in between, I'll have to subtract that 15.87 from the 84.13. After I do that subtraction, I get 68.26. So the percent of values that lies in between the interval 115 to 135 is going to be approximately 68%. This is going to be the same problem, only different numbers. So instead of from 115 to 135, I'm going to try to test from 100 to 150. After I find out the probability from 100 to the left tail is going to be 0.62, and the probability from 150 to the left tail is going to be 99.38. I do the appropriate subtraction, and I get the probability is going to be 98.76. So the percent of values in the interval 100 to 150 to the nearest percent is going to be 99%. So the confidence interval here is going to be 99%. Here I want to work backwards. So I want to find the interval from the interval so that in the middle, the percent of values in the middle, the probability is going to be 95%, so 0.95. In order to do that, I have to see that if my middle part is going to be 95%, then my two tails on my left and my right, those non-shaded region, it's going to be the rest of it, the rest of the 5% divided in half, because I have two parts, I have two tails. So I'm going to have 2.5% on my left side, and I have 2.5% on my right side. But because of my z table goes from the left tail to whatever threshold, I'm going to use 2.5%, and I'm going to use 97.5%, because that's the table that I'm using. So if you're using a different table, you may need to set the problem up differently. That's where that picture at the top of your table comes in handy. So after looking up the appropriate probabilities, the appropriate percentage values, 0.025 and 0.975, I get the z values are going to be negative 1.96 and positive 1.96. So those are the z values. Now those are going to be that's going to be equal to that formula, x minus mu over standard error, or that critical value minus the mean over standard error. So negative 1.96 minus 125, or x minus 125 over 10, that's going to be equal to negative 1.96. X minus 125 over 10 is also going to be equal to positive 1.96. So I have to solve for those x values. And after I solve for those x values, I get 105.4 and 144.6. So that's going to be my confidence interval. My confidence interval is going to be from 105.4 to 144.6. Now the same thing here, only instead of 95%, my confidence interval here is going to be 50%. So my probability from in between, in the middle, is going to be 50%. So in my left tail, and my right tail, those two tails are going to have to add up to the remaining percentage, so another 50%. So one tail is going to be 25% and the other tail is going to be 25%. And again, since I'm using a z-table that goes from the left tail all the way up to a threshold, I'm going to have to use 0.25 and 0.75. So if I look that up in the table, I get my z value is going to be negative 0.675 and positive 0.675. And like before, I set that equal to x minus 125 over 10 because it's my critical value that I'm looking for, minus 125, which is the mean, over the standard deviation, which is 10. After I solve for x, I get x is equal to 118.25 all the way to x is equal 131.75. So that's my confidence interval, 118.25 to 131.75. And that's it for this question. Again, the key thing is whenever you're using the z-table, look at that picture so you know what those numbers on the table represent. You need to know whether it represents from the left tail all the way to your threshold, or from your threshold to your right tail, or it could be from the median or the middle to your threshold. So you'll need that picture to determine whatever those numbers represent. And then whenever you're doing these type of problems, I can't stress enough that you'll need to draw a picture. Drawing that picture will help you so much when solving these type of problems. And that's it. Thanks for watching.